Okay, chapter 10. So chapter 10, we're going to start working with integrals in terms of their application instead of just the inverse of the derivative. So in chapter 9, we learned about antiderivatives or integrals being the inverse of our derivative. We were working backwards. So differential calculus, stuff we were working on, chapters 1 through 7, arose from the tangent problem. Remember way back in chapter 1, we were like, how do you calculate the slope of a tangent line? And then that's where differential calculus came from. Now we're looking at integral calculus, and it arose from the problem, what is the area under a curve? So if we've got some funky little curve happening and we want to know the area under it, how do we calculate that? So this is what we're going to look at today. So first of all, remember back in chapter 9, we looked at what the indefinite integral was. So remember that the indefinite integral was the integral of my function in terms of x was equal to the antiderivative, capital F of x plus c. So it was equal to some family of functions because of the constant. So today we're looking at what is a definite integral. I was going to switch the color on that. Sorry, I'm just being silly, but I like to change my colors. Okay, so the definite integral now is going to be defined on some sort of particular interval. Okay, so now we're going to have numbers on either end of that skinny s integral symbol. Okay, so this is now saying take the integral from a to b of your function, where a and b are real numbers. Okay, so that means I can have positive and negative interval boundaries. All right, so it's defined by this rule. The integral of f of x in terms of x from the boundary a to b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. This means we're going to get a numerical answer. Okay, so instead of getting a family of answers, we're now going to get a numerical answer. Okay, where big F of x is any antiderivative of little f of x defined on that interval. And so common notation for the f of b minus f of a is to use this in square brackets evaluated from a to b. I like that one a lot. I'll probably use it a little bit. And so there it is. There's our definition. So let's give this a try. Okay, so we're evaluating this function from 1 to 4. Those are our boundaries. Okay, so the integral from 1 to 4, I'm just going to rewrite this out, 3x squared minus 2x to the negative 1/2 plus 1 dx. Okay, is what color? Equal to. So the antiderivative of 3x squared. So we have 3 in the front, x, add 1 to 2 is 3 divided by 3, minus 2x, add 1 to this fraction, so that's like 2 on 2. So 1/2 divided by 1/2 plus x plus c. And then I'm going to tidy that up. So I get that is equal to x cubed. Okay, so 2 divided by 1/2 is 2 times 2, so minus 4x to the 1/2 plus x plus c. And now I'm going to evaluate this from 1 to 4. So this is my f of 4 minus f of 1 that I am now going to do. And that just means I'm going to put 4 in for my x's. And x to the 1/2 is just the square root, so I'm just going to write that as square root plus 4 plus c. All of that, subtract. Now put in the 1 cubed minus 4 times the square root of 1 plus 1 plus c. Okay, so this is essentially the f of 4 minus f of 1 that we're going to be doing, or are in the midst of doing. Okay, so what do we have here? We have 4 cubed, which is 64. Mental math day, minus 4 times square root of 4, 8, plus 4 plus c, and then minus 1 minus 4 plus 1 plus c. Okay, so you've probably punched this all into your calculator, and we've got 60 plus c minus, we've got a negative 2 there. Yes. And then be careful, there's a subtract c there. Watch the subtract, right? So it's all the way through. And what should happen is that those c's should cancel out, and the answer to the question is equal to 62. Okay, so the definite integral of this function on the boundaries from 1 to 4 came out to be 62. So what does that actually mean? What did I find? Okay, what is the application to this? So one of the most important uses for the definite integral is in the calculation of areas where our boundaries may not be straight lines, like the diagram below. Okay, so we've got this function f of x, that's a curve, and then I'm trying to figure out what is the area below the curve. So the upper boundary is my function, that curvy part. The lower boundary is actually my x-axis, okay? And then I have a left boundary at A and a right boundary at B. So I'm trying to figure out what is this area. And it's defined as A of B, which I just kind of colored over top of, sorry. If I had this as just some ordinary geometric shape, or a bunch of shapes, then I could just use my geometry formulas. So an area of a trapezoid, an area of a rectangle plus the area of a trapezoid, whatever it was. But because I have this curve happening, okay, that's the problem. That's where the integral calculus comes into play. Okay, and so because we're finding an area defined on an interval, we use this notation A of B. So you use the left boundary as the number that goes in. So in our previous question, if that was actually an area question, then it would be, this one would be defined as A of 4 is equal to 62 units squared. That's what would happen. Okay, but this was not asked as an area question. This was just asked as a calculation of a definite integral. So you'll have to be careful to figure out, is this an area question? Should I have units? Or is it just a plain old calculation of a definite integral? Okay. All right, so if f is any antiderivative of the positive function f, the area under y equals f of x from the defined interval a to b is A of b. So note the notation here. So we don't have the little a. So you always use the right boundary here. That's your right boundary of my function is defined as the antiderivative of b minus the antiderivative of a. Okay, so there's a couple of key things about this. First of all, remember that the antiderivative is a family of curves, each with a different constant. Since f is any antiderivative of little f, we can choose to use the antiderivative where c equals 0, or like we just saw in the previous question, you end up with f of b plus c minus f of a minus c. The c's cancel, right? Once you distribute, pardon me, once you distribute the subtract through, the c's cancel. So you can also just think of it that the c's are canceling, and then you just don't need to write the c's out. So that's the gist of this piece, is that I don't need to see c when you're calculating the areas or definite integrals. So when we're working with numbers, I know the c's just cancel. So I can assume that we're just using c equals 0, or that I know that you know that the c's cancel. That's what that's all about. The second part is actually really important here, so you might want to highlight it. The term under. Okay, so this under is understood in math to mean the area between the curve and the x-axis. Between the curve and the x-axis. Okay, so we could actually be underneath the x-axis. So we could be looking at some parabola or something where we're just looking at this little piece. That's maybe not the best, but you could think of it as a it doesn't really matter. It's just that it could be the piece between the x-axis and the curve. So the curve could end up being below the x-axis. That's the part that I'm trying to get to. So hopefully I didn't blotch that too badly. Whew. Okay, example number 2. Let's actually calculate an area. Okay, first thing, my recommendation is to draw your picture. So we're going to determine the area under the parabola. So remember, under is between the x-axis and your curve from x equals 2 to x equals 4. So I have a parabola, and it's been vertically translated 2 units up, so it's looking something like this. Okay, it doesn't have to be perfect. It's just to get an idea of where your areas are. And then we are evaluating it from 2 to 4. So we're looking at calculating this area. So the area of 4 is equal to the integral from 2 to 4 of my function in terms of x. There's my notation. Then I go ahead and take the antiderivative. So the antiderivative of x squared is x cubed on 3 plus 2x. And I'm not going to write my plus c. I'm now going to evaluate this from 2 to 4. So I get the area of 4 at 4 is 4 cubed on 3 plus 2 times 4. Subtract 2 cubed on 3 plus 2 times 2. And what numbers do we get? Did you mental math this? It's not pretty, it's fractions. Okay, so we have 88 on 3, subtract 20 on 3, and that is equal to 68 on 3 units squared. Yes, you do need to include units squared when it is an area question. So this is equivalent to this notation of a of 4 is equal to 68 on 3 units squared. Okay? So the difference between a definite integral and an area question is just in the notation. We have this extra little piece to include, and then we have units at the end. Okay, so feel free to pause the video here and give this one a go. Can you remember how to graph sine x and to figure out where those boundaries would live? And I'll come back and we'll go through it in video number 2.